1733. The Count of Buffon drops a needle onto his wooden floor. He watches it land and wonders, how often should it cross one of the cracks? Hiding inside his idle question is what I think is one of the strangest appearances of pi in all of mathematics. To catch pi in the act, let's rebuild his experiment. Here is his floor. Parallel cracks 1 unit apart. Nothing else about the floor will matter. And here is the needle, exactly 1 unit long, the same as the gap. So, let's drop it. Sometimes it lands across a crack, and if we drop it again, sometimes it slips cleanly into a gap. Same throw, same floor. 2 different fates. What if we simply experiment our way out? 10 needles and a tally. 7 cross, so 70%? 10 more. This time, 5. A handful of throws proves nothing. We want the exact number, and for that we need theory. So we ask the only sensible question. What is the probability that a dropped needle crosses a crack? No tricks. A perfectly ordinary floor. A perfectly random throw. What would we guess? 1/2? 2/3? Whatever we guessed, the true answer will turn out to contain pi. And that strange fact will hand us something better, a way to measure pi, using nothing but a floor and patience. Let's start from what we know, a coin. 2 outcomes, 1 favorable, 1/2, done. A die, 6 outcomes. We count the ones we're after. Probability is counting. Favorable over total. Now let's try to count the ways a needle can land. Its center can sit anywhere in the gap, anywhere at all, not 10 positions, not 1,000, a continuum. And at every one of those positions, it can point in any direction. 2 dials, both infinitely fine, position and angle. So, favorable over total has become infinity over infinity. The counting rule we grew up with just died. We don't need a bigger count. We need a different way to see a needle. The Count, the story goes, kept staring at his floor until the floor became a picture. Let's look closely at one landed needle. Almost everything about it is noise. Which board it landed on? Irrelevant. Every board is the same. But let's not hand-wave that. Here is the bookkeeping. 4 gaps on this floor. The needle lands in each with probability 1/4. And within its own gap, every needle tells the same story, the same geometry, just shifted. So we can write it out. The law of total probability. The overall chance is the average over the 4 gaps. 4 identical stories. And the average of 4 equal numbers is that number. Watch them collapse. 4 gaps, or 4 million. The whole problem lives inside a single gap. How far left or right? Also irrelevant. The cracks run forever. Strip the noise away and only 2 numbers decide its fate. First, how far its center sits from the nearest crack. Let's call it X. It runs from 0, sitting right on a crack, to 1/2, dead center in the gap. Why stop at 1/2? Slide past the middle and watch the measurement. The nearest crack is now the one above. From that crack's point of view, the same story begins again. Nothing new ever happens past 1/2. Second, the angle it makes with the cracks. Let's call it theta, from 0 up to a right angle. And why stop at 90? Tilt past it and watch. We simply repeat a case we already have, mirrored. 120 degrees reaches exactly as far as 60. 0 to 90 is the whole story. Position and tilt. X and theta. Nothing else. And here is the move that cracks the problem open. What if we forget the floor and build a map of every possible needle instead? 1 axis for the angle theta, 1 axis for the distance, x. This rectangle. Every point inside it is one way a needle can land. This needle, steep, far from a crack, is that point. Now let's slide the needle one full board upward, a different place on the floor, but the same x, the same theta, the very same point. Infinitely many needles collapsing onto each point of the map. That is the compression. This one, flatter and closer. That point, lower and to the left. And a needle lying exactly on a crack sits here, on the very floor of the map. Watch them travel together as the needle moves. An entire infinite floor, compressed into one finite rectangle. It is worth sitting with that for a moment. Every outcome of a physical experiment laid out flat on a page. And now the phrase "dropped at random" finally means something precise. Every point of the rectangle, equally likely. Equally likely points. So, what if we try counting again, right here on the map? Let's make a simplifying hypothesis. Suppose the needle could only land at 10 fixed tilts, and at only 10 fixed distances from its crack. 10 tilts, 10 distances, 100 possible needles. That we can count. So we give each combination its own little cell on the map, a needle at that tilt, at that distance. And we let each little world play out. 64 of the 100 cross. So, around 64%. The hypothesis was crude, so we refine it. 1,000 possible needles. 63.7. Refine again. The needles melt away entirely. 63.65. Still moving. A finite grid will never settle it exactly. There is always more rectangle between the grid lines, but something far more valuable has appeared. Look at the shape the crossings carve out. The border between hit and miss is a clean, smooth curve. If we understood that curve, we wouldn't need to count at all. So, when exactly does a needle cross? Here is a needle, next to its nearest crack. When exactly does it cross? The needle is 1 unit long, so each arm reaches half a unit from the center. And notice, the other crack sits at least half a unit away, at the very limit of the arm's reach. Only the nearest crack is ever truly in play. Now the crack doesn't care how long the arm is, it cares how far the arm reaches toward it, vertically. As we tilt the needle, that vertical reach changes. Nearly flat, the arm is long, but its vertical reach is almost nothing. Upright, the full half unit. In between, look, the arm is the slope of a right triangle. Its vertical side is 1/2 times the sine of theta. Let's check it. At 30 degrees, sine is 1/2, so the reach is 1/4 of a unit. That is all sine ever was. The vertical shadow of a tilted stick. So the needle crosses exactly when the nearest crack is within reach. When x is at most 1/2 sine theta. One line of mathematics for the whole messy physical event. And notice what it does not depend on. Not the board, not left or right, exactly as promised. Now let's draw that condition on the map. The curve. X equals 1/2 sine theta. Below it, the crack is within reach. Every one of these needles crosses. Above it, too far. Every one of these misses. Let's test one point. 60 degrees, x equal to 0.2. The reach is 0.43. The crack is in range, and sure enough, the point sits below the curve. And there it is, the curve from our counting experiment. Every possible needle sorted by one sine wave. The chaos of a tumbling needle is gone. What remains is geometry. And geometry we can measure. Every point equally likely means the probability is a ratio of areas. The crossing region over the whole rectangle. The rectangle first. Its width is pi/2. Its height is 1/2. Area, pi over 4. Let's pause and look at what just happened. Pi has entered the problem, and there is no circle anywhere in sight. Or rather, there is. An angle is a piece of a circle. The circle was hiding inside the word direction all along. Now the crossing region, the area under the sine curve, and the area under a curve is exactly what an integral measures. This one comes out to exactly 1/2. No approximation. The corners of the picture agree. A flat needle almost never crosses, and an upright needle always does. Its half-unit reach spans exactly the worst case. So the probability is 1/2 divided by pi over 4, 2 over pi. About 63.7%, right where our grid was pointing. And for any needle of length L on boards of width T, the same picture gives 2L over pi T. Now for the twist that made this little puzzle immortal. What if we read the equation backwards? If the probability of crossing is 2 over pi, then pi is 2 over the probability. And a probability is something we can measure. By experiment. Drop needles, count crossings, divide. The floor has just become a scientific instrument, an instrument that measures pi. Probability has left the gambling table and become a way of measuring the world. Let's run it. 100 needles, 62 cross, 2 times 100 over 62, 3.23. Crude. But watch what the law of large numbers does. 500 needles, 319 crossings, 3.13. 2,000 needles, 3.137, and still closing in. Every single needle is a tiny, terrible estimate of pi. Averaged by the 1,000, they sharpen into the real thing. The bounce is randomness. The slow drift toward pi is law. Today this is called the Monte Carlo method. It runs inside every physics engine and every bank. The Count got there with a flaw, 2 centuries before computers. Honest convergence is slow, though. Each new digit of pi costs about 100 times more throws. One warning from history. In 1901, Lazzarini reported 3,408 throws and got pi right to 6 decimals. 6 decimals, dead on the line. That is a man who knew when to stop throwing. Honest needles converge slowly, but they do converge. So, the Count's question has fallen. A dropped needle crosses a crack with probability 2 over pi. And folded inside that answer, pi, extracted from a wooden floor. One last door left open. Let's clear the floor. What if we bend the needle, same length one, folded at a right angle, and rain it down again? Watch its estimate in blue. It wanders differently and settles on exactly the same number. So the shape never mattered, only the length. On average, twice the length means twice the crossings, which means the average count is some constant times the length. But which constant? We ask the one shape that leaves nothing to chance. A circle, exactly one gap wide. Wherever it lands, however it slides, it crosses exactly twice, always. And its length is pi times its diameter, pi. So 2 equals the constant times pi. The constant is 2 over pi, and since a straight needle of length 1 crosses at most once, its average count is exactly its probability. The circle closes the case.